Another place that you probably understood where logarithms are used at are on earthquakes and how we are able to kind of judge the magnitude of comparable earthquakes. And we developed the Richter scale, just like we developed a pH scale to understand logarithms for acidity of a base or acidity of a fluid or a liquid. Likewise, we developed a Richter scale, which is a logarithmic scale to understand the relative powers of earthquakes. And it's described as this, where it equals the logarithm of the intensity of an earthquake compared to an initial intensity, an earthquake that's barely felt. Well, I don't remember it, and maybe you don't, but maybe you have a relative that lived through San Francisco in 1906, where the earthquake was 10 to the 8.3 times more powerful than one that's felt. And just think about that. It was 10 to the 8.3 times more powerful than a one that's barely felt. So if that's what happened, what did that read on the Richter scale? So let's go ahead and look at our model right here. I'm comparing it to an initial light earthquake. This one's 10.83 times stronger than this. So I would write that as 10 to the 8.3 times the intensity of the smaller one because it's 10.83 times as much. If I solve that down and reduce that down, notice the I sub zeros, which is a relatively low intense earthquake. Those can factor out of both the numerator and the denominator left, and the denominator. So I'm left with the log of 10 to the 8.3. So do you remember how we can solve that based on some of our properties? Well, first of all, understand that it's a common log. And if that's the case, there's an understood 10 as its base. Do you remember a property from a couple of while ago where we have the base and the number were the same? The result or the log was just the exponent, which is 8.3. So on the Richter scale in 1906, the earthquake read 8.3 on the Richter scale. What does that mean? That means it was 10 to the 8.3 times stronger, not just 8.3 times stronger, but 10 to the 8.3 times stronger. And if we just wrote that out for a little bit, what is 10 to the 0.83? That's got 10 with 8 zeros after it. I got the decimals the wrong spot. And so it's that many times stronger, not 8.3, but that times stronger. That's why we use logarithm scales to help us have an understanding of how large some of the things that we observe in the real world around us, how do we compare them with numbers that make sense? So when you look at a Richter scale, understand what happens. An 8.3 compared to an 8.3 or 8.4, what if it was just read 8.4? That's 10 times stronger. Wow.